machine learning, causal inference, and nonparametric or semi-parametric.
All right, thanks everybody. Okay, so maybe we can do a quick recap and remember where we were before lunch. So we're trying to understand optimality for parameter estimation in these big non-parametric models. And what we know is kind of the classical theory from Kramer-Rao lower bounds, which tells us something about optimality in parametric models. And so we are using this device first used by Charles Stein, which is the submodel. So this says you just look at some smaller model of the bigger non-parametric model, and you find a minimax lower bound in the smaller model. This automatically has to be a valid lower bound in the bigger model. And now the whole game is to see if we can come up with a clever choice of this submodel so that it's actually a meaningful lower bound. It's something we have some hope at attaining. Okay, so we're thinking about, this is the picture of Stein I love. So here's the kind of submodel you can keep in your mind, which is just think of this dp as a density of the observations multiplied by 1 plus epsilon times some function h. And this function h can be generic, it's just some mean zero function. And somehow this choice of h is going to determine how informative this submodel is, how informative the lower bound in this submodel is. And so we're going to try to pick a smart choice of h, which gives us a meaningful lower bound. Okay, so for any one of these submodels, we can just use the Kramer-Rao lower bound, which is, again, the derivative of the parameter squared over the variance of the score. And so now the idea is we want to find the most informative lower bound, which is the biggest lower bound. So we want to try to maximize this quantity over all choices of submodel, basically. So, for example, in this previous submodel I showed you, this score is just that function h. So this denominator function will just be the variance of this choice of h that you give me. But for any h, this will be a valid lower bound, as long as it's mean zero, so that I get a valid density. Okay, so that's the task. So basically, for any submodel that you give me, the variance of the score is easy. That just pops out of the form of the submodel. Now the question is, what do I do with this numerator? Because I'm trying to maximize this Kramer-Rao lower bound. The denominator is easy, just comes out of the form of the submodel. The numerator is a little less clear what I should do with this guy. For this, we're going to impose some smoothness condition on the functional that we're targeting, which is a meaningful restriction. It's imposing enough structure for us to be able to say something interesting. But it's quite generic, and it will hold. It will be a valid restriction for lots of different kinds of causal quantities that we care about. Okay, so what we're going to assume is that this functional that we're going after, this parameter psi, satisfies a distributional Taylor expansion. So this really is just like the idea of a Taylor expansion, but on the functional scale, thinking about functionals as maps from distributions to, say, reals. So if you squint at this, this looks like a usual kind of Taylor expansion where I look at the function at one distribution versus another, and then this looks something like the difference between these distributions multiplied by something like a derivative, and then some remainder from this approximation, this linear approximation. Okay, and yeah, this is sometimes called a von Mises expansion. But intuitively, this is really just a standard Taylor expansion, but on the distributional, on the functional scale, viewing functionals as functions of distributions. Okay. I'm going to be a little bit vague about this, the remainder of this approximation, this linear approximation in this Taylor expansion for now, but we'll look at some examples later, depending on time, and be a bit more explicit about this. But I want to be, I don't know, maybe more heuristic and just give people a sense of what the idea is before worrying about specifics. Okay, so we're going to impose this smoothness, and it's important to note that this is a property of the functional. It's a property of the parameter that we're going after. It doesn't have anything to do with the distribution that we're sampling from or anything like that, roughly speaking. Okay. And yeah, this kind of expansion was used by von Mises. It's discussed here in this book by Van Zagel in the 80s. Again, I want to point to this kind of stuff because I want to make sure people realize that a lot of these ideas have been around for decades. You can see them in this really kind of horrible typeset book, but it's right here, this kind of expansion. This Van Siegel book, and Van Siegel more generally, I think doesn't get the kind of credit that maybe he deserves for these kinds of ideas. And I felt guilty about including a picture of Stein, so here's a picture of von Mises and Van Siegel. This is the only one I could find of Van Siegel. He just passed away like 5 years ago, I think. Okay, so yeah, intuitively this is just imposing some smoothness on the parameter. And this expansion is telling us something about how the parameter changes when I change the distribution that it maps from. And to me, this expansion is really what drives everything in the tutorial. It drives both the lower bound story. It allows you, once you can prove that this expansion holds for some choice of that derivative term, it immediately gives you minimax lower bounds, and we'll see that in just a minute. But it also tells you how to construct estimators. Somehow from this expansion, it tells you something about how to correct bias. And it gives you something about the conditions that you need to use to analyze these estimators. So somehow all three of these different branches that go through this whole tutorial are driven by this one expansion. So this is really important. And you can, again, get some intuition by thinking about like the discrete case where the distribution is just takes some finite number of values. Like you've got discrete covariates, for example, and discrete outcomes. And then this is just a usual vanilla Taylor expansion. There's nothing fancy going on at all. Okay. So there's there are lots of different ways of thinking about this expansion. Another way is what's called pathwise differentiability. This may be a slightly more rigorous, less heuristic way of thinking about this. Which expresses the derivative of the functional on the left-hand side, evaluated at some particular submodel, as an inner product between this derivative term in that Taylor expansion and the score of the submodel. But to me, this is really, intuitively, it's the same as that expansion. There's nothing really extra in this notion of pathwise differentiability, and you could show that this holds by just evaluating that expansion at p epsilon and p and taking a derivative, and you'll arrive exactly at this expression. So you'll maybe see this more in the technical literature, but to me it's really just exactly this Taylor expansion. And the fact that this remainder in the expansion is second order, so what I mean by that is this remainder, it depends on these two distributions, in this case p and p epsilon, or in general, whatever two distributions you're evaluating the expansion at. And when I say it's second order, I mean it depends on like squares of differences between these distributions or products of differences. And what this means is that when you take derivatives of this remainder term, you get 0, and this is really like just another way of thinking about name and orthogonality, which is another common way of thinking about this kind of structure. So yeah, to me these are all the same, and I like thinking about things that are simple, so Taylor expansions are kind of my preferred way of thinking about this. And yeah, what I said before is that this is really crucial. It drives everything. It gives us, we'll see that once you derive this expansion, you immediately get a lower bound, a minimax lower bound for your problem, like for free. Once you have this, you're basically done. So it gives you this lower bound story, but it also gives you some recipe for constructing estimators, because everything will hinge on this derivative term, which is the influence function of this parameter, or the influence curve. That's what we call this derivative expression. And this is exactly what we use to bias correct plug-in estimators. It's exactly the quantities that appear in like AIPW estimators and doubly robust style methods. So it gives you there are explicit recipes for constructing estimators once you have this expansion. And then proving that this remainder term is second order, which is really showing that this expansion holds, is really analyzing the bias of these estimators. So once you have this piece figured out, you've really solved all three of these problems all at once, which is pretty neat. And yeah, really the key part in all of this is the remainder term and this function here, which is like a derivative term of this expansion, which is the influence function of this parameter, influence curve or gradient. You'll see all this different terminology. But it's like the derivative, it's expressing how the parameter is changing kind of locally when you move from one distribution to another. Okay. And so yeah, here I want to maybe distinguish, like I mentioned in the first hour, the difference between this influence function and the influence function I talked about before, which is for an estimator. So here there's no data or anything. This is a purely functional analysis kind of perspective, right? I don't have samples, I don't have sample size or anything. This is just a property of this parameter expressed as a functional. And so this is different from the influence function we talked about earlier, where we said an estimator asymptotically behaves like a sample average of something, and that something is the influence function of the estimator. So unfortunately, these have the same names, and sometimes they coincide, so it kind of makes sense that they have the same name, but they're, to me, different quantities. You can have influence functions for parameters or influence curves, which may not be influence functions for any estimators, because maybe the regularity conditions that you would need for an estimator to be root inconsistent wouldn't hold, for example. So I would think of these as kind of like possible influence functions for possible estimators, but they may not actually be influence functions in practice. They may not be attained as influence functions by particular estimators. So they're kind of distinct concepts. Okay, and so now, once we have this expansion, this kind of paves the way for doing this optimization over all these submodels in a very simple, clear way. It allows us to optimize over all these submodels, which sounds like a kind of difficult task at the start of things, very easily, just using the structure of this, this expansion. And so you can kind of see this here. So this quantity is just this derivative squared over the score. This is that Kramer-Rao lower bound for the submodel. And what I want to do is optimize this. I want to find the most informative one and pick the one that maximizes across all submodels. I'm going to take a supremum over submodels. And so if I pick a particular set of submodels, like those ones I showed you before that are really simple, that just multiply the density by 1 plus epsilon h, then I can just optimize over that choice of h. And intuitively, maybe it feels like I've lost something in restricting to a choice of submodel, but it's important to remember that any choice of submodel will give me a valid lower bound, because it will always be a submodel of the larger model. And so I can make a pretty simplistic choice, and as long as it turns out to be an attainable lower bound, then that's all we care about. Any choice will be a valid lower bound. It may not be a good one, but it turns out that these simple choices end up being attainable and being useful. All right, so we can just optimize over this choice of h, and what we saw is for this submodel, the denominator is simple. It's just the variance of that h function. And then under the that Taylor expansion kind of property of the functional, if I use the pathwise differentiability version of it, I can replace this derivative with an inner product, which is just a mean of a product of two things, which is the mean of the square times that derivative in the expansion. So I just make that replacement here, which again is just using that Taylor expansion. That's all, essentially. And now by Cauchy-Schwarz, this is upper bounded by just the variance of that, whatever that derivative term is in the expansion. And then as long as I can pick h to be equal to that derivative, then this bound will be attainable. That's a particular submodel, which will give me a valid lower bound. And this argument shows you that it can't be beaten. I can't make the Kramer-Rao bound larger than this. Okay. So the basic story here is once I have this approximation, I can get a very simple form for this Kramer-Rao lower bound. I can optimize over all these submodels very easily. And it turns out that the Kramer-Rao lower bound is just equal to the variance, or the best Kramer-Rao lower bound across all these submodels is just equal to the variance of that function that appeared in my Taylor expansion. So that tells me, this is what I said earlier when I said that once you have this expansion, you already have a minimax lower bound. And that's because of this argument. So the variance of that derivative term, and that is just a function of your observations, the variance of that thing is a minimax lower bound in this local asymptotic sense. And this function is called the, again, influence function or influence curve or gradient or efficient influence function. So from this argument, which present it a little bit heuristically, we now have a benchmark. We now know that no estimator in a non-parametric model can have an error that's better than the variance of this function, which again comes from this approximation, this Taylor expansion, divided by n in this local asymptotic minimax sense. So now everything kind of hinges on deriving this expansion. If I have this expansion, then the variance of that derivative term immediately is a lower bound. Any questions about that? It's just a formal statement of the property that holds here, this local asymptotic minimax sense.
So the way that this is framed in like Ciatis, isn't it more about like constrained irregular asymptotically linear estimators? Is there a reason why you're focusing on this? Could you say something about the difference between those?
Yeah, that's a good question. Yeah, there are lots of different ways you can express this kind of like benchmark result. And yeah, Caleb was mentioning this one that instead restricts the class of estimators and then says something about this among the class of all regular asymptotically linear. I guess I feel like, yeah, the reason I'm focusing on this is just because I think the local asymptotic minimax kind of perspective or just minimax perspective period is a little more clean to me personally, but because here there's no restriction on the estimator at all, which I think I just prefer. It's nice to think of, like, you can think of all possible maps from the data, and it doesn't matter how complicated they are or what, this result will apply to these, but yeah, that's an alternative way to frame this kind of result.
But how can that be that there are no restrictions in the estimator? Because, you know, Ciatis talks for a long time about all these super efficient things that are kind of degenerate in weird ways, and presumably, like, that's not included. Like, you somehow rule this out, like, when you do this, right? One way or the other.
Yeah, so we're taking a soup over all distributions, so
okay, that's what does it.
Yeah.
Okay. So it's not really correct to say that there are no restrictions in the estimator, it's just that they naturally fall out of the way you've written this down, basically.
Well, I guess what I mean is this infimum over all estimators is not restricted. It's truly an infimum over all possible maps from the data. Yeah, but yeah, they're super efficient things would be hit by the supremum, so it would fall out that way. Okay, so yeah, there's a long history here. There's a lot of this kind of argument was developed, yeah, from Stein in the 70s by people like Dragamov and Hespenski. This is from the Bickel, Boston, Ritov, Wellner book, which has some nice discussion of the history. Okay. All right, so what do we have here? We have a minimax lower bound. This tells us intuitively that no estimator can do better than something that's rooted and consistent with a variance equal to the variance of whatever this object is that appears in this expansion. And this expansion you should think of as being like functional specific. So every parameter has a different derivative term in it. The variance of this derivative term is always going to tell us, it's going to give us a minimax lower bound. Okay, so this is kind of a clean lower bound story. We now know that no estimator can do better than something, but we have some remaining questions, which are, one, how do we actually derive this expansion and come up with this function phi? And it turns out there are some very simple tricks for doing this. And then a second question is, okay, once I have this expansion, how do I actually construct estimators that can possibly achieve this bound and will therefore be minimax optimal? Okay. And so here I just want to talk a bit about how to derive that function phi in the expansion, like how to show that this expansion holds. And there are a few different ways I know of for deriving influence functions. So the first way is to use this pathwise differentiability expression, which says that a derivative of the functional is equal to some inner product. It's like an integral of a function times the score. And so you can write down a submodel, you can compute the derivative. Maybe I'll show this. Yeah, you can write a submodel down, compute this derivative. That's a nice kind of forward-thinking, constructive analysis, it's easy to do. But then you have to somehow massage what you get into some product expression, and that can be challenging if the functional is complicated. This is what I did when I was a grad student, and I spent tons of time doing this kind of argument. And so there's another way that I started using over time, which is much simpler. You can do the calculations in your head. It takes like minutes, which is just to take derivatives. It's basically like this Gateau derivative approach, which I think I'm going to skip in the interest of time, but people maybe have seen before. But it's really to treat influence functions like derivatives, because they're derivatives in these Taylor expansions, and then just use all the rules from elementary calculus with them. And so it simplifies so many of these calculations. I think this is one of the more useful things that can maybe come out of the tutorial for people. I feel like I would have saved 90% of my time as a grad student if I knew this sort of thing. So let me show you some of the calculations quickly. This is for the expected density. So again, we can just use that submodel I wrote before where I take the density and multiply it by 1 plus epsilon h. It's easy to compute the derivative of this. Now I need to take that expression and write it in terms of an inner product. And with the expected density, this is really easy. You can do this in a couple lines. Some regularity conditions, you move derivatives inside integrals, replace derivatives of densities with derivatives of log densities times densities, do a little bit of rearranging, and then you get some expression that looks like the score from your submodel, which is right here, times something. And whatever that something is, that's that function that we're trying to find. And so that tells us that this is the influence function for this parameter, 2 times the density with some centering. And you can then, once you do this, you can write out what that remainder is. It's the difference in the parameter minus the inner product. And it turns out that the remainder in this case for the expected density is minus the squared L2P difference between the two distributions you're looking at. So this shows you what I mean by this remainder being second order. In this case, it's a squared difference between distributions. Okay, so for this expected density example, you don't need any of these tricks. It's extremely simple. You can do it in 3 lines using just kind of solving this integral equation. But for more complicated parameters, it becomes a pain. So let me show you. So here's the tricks I use. I'm going to pretend the data are discrete. This is the first trick. And this just makes it so that some simple fundamental objects like regression functions have influence functions. So in general, in like continuous settings, those objects will not have influence functions. They are not estimable at root n rates. What we say is that they're not pathwise differentiable. And so I pretend the data are discrete so that they're like means, and I can estimate them at root n rates, and they have influence functions. They're nice regular parameters. The second trick I use is to treat influence functions like derivatives. So this means I can use like product rules. So if I want the influence function of a product, I just take the influence function of the first times the second plus the first times the influence function of the second. The very simple rules from calculus, chain rules and so on. And then the third thing that I use, the third trick, is to use like these building block influence function results. So I use the fact that, for example, the influence function for a regression function in the discrete model just looks like a residual multiplied by an indicator scaled by a probability. And this result you can check, or you can just use it as a tool in these calculations. But this one's easy to check using the more rigorous approach. So this is the heuristic strategy I use, and yeah, I think once you get used to doing this, you can do it in your mind very easily in like a minute. You can start to see what influence functions are going to be just by looking at them, or at least that's how it works for me. Whereas with the other approach where you're solving this integral equation, I feel like it's really hard to see what's going on. You have to massage things and get it right. Okay, so let me show you for the average treatment effect. So I take the regression function, say for the treated, and standardize it to the marginal covariate distribution. The influence function looks like this expression lots of us have seen before. Some inverse weighted residual plus the regression function minus the parameter. And this is exactly what you average up. This first piece is exactly what you average up to construct doubly robust style estimators that are popular now. So that, yeah, this is maybe a canonical influence function to keep in mind in all of this discussion. It's a function of the observations, so it's a function of covariates, treatment, and outcome, and it depends on nuisance parameters, so regressions, propensity scores. And in this case, that remainder of that Taylor expansion looks like a product of differences between propensity scores and regression functions. And now maybe you can start to believe what I said earlier about the fact that this expansion drives not only the lower bound story, but also the upper bound story. It tells you how to construct estimators, because estimators look exactly like averages of this estimated. And it also drives the analysis of these estimators, because when you derive that remainder of the expansion, you're really just analyzing the bias of the estimator. And this, you'll recognize if you've seen doubly robust estimators before, is just the bias of these kinds of estimators. They look like a product of errors. That's why they're called doubly robust. Okay, so here's in the paper that I showed you at the start, the review paper, I give a proof using this like integral equation approach, and it's 4 pages. It's not bad proof, but it's kind of annoying to go through, and it takes 4 pages of work. And if you use these tricks, you can do this in like 2 or 3 lines, and I can do it right here in 1 minute. So let's do the influence function for the average treatment effect. So I'm going to pretend things are discrete, so I can write this expectation as just a sum over the different x values. So this is my parameter in the discrete case. I just replaced an integral with a sum. And now I'm just going to use these calculus tricks. So I can move derivatives inside sums. So I'm going to move the influence function operator inside this sum. And now I've got a product, so I'll just use the product rule. And so I can write this as the influence function of the first guy times the second, plus the first guy times the influence function of the second. And now I'm going to use my last trick, which is I'm going to use the fact that the influence function for a regression function looks like a residual with some indicator scaled weighting. And the influence function for this, which in general would be some covariate density, here is just a probability, which is just an expectation, which is a special case of a conditional expectation, so I can use the same thing. It looks like a residual. So again, you could prove those building block results, or you could just use them as tools and check that everything works. Okay, and now I'm done. Now this is like a 2-line construction of this influence function. Now I just evaluate the sum and rearrange, and I get that influence function from before. So it's very constructive. You just turn the crank and use these tricks, and you get out the influence function. Again, you can start to see, because you can do the product rule in your mind, you can start to see what the influence function is going to look like for simple enough functionals.
So this kind of transition from discrete to continuous, is there any formal justification of that?
Yeah, so the way I think about it is this procedure, I mean, I think you could probably prove this works in some generality. I haven't done this, but maybe someone has it I don't know about. But yeah, the way I think about this is that this is a heuristic for coming up with like potential influence functions. And then once you have a guess, then it's super easy to check that it's a valid influence function, because then you just check that that approximation holds. The hard part is coming up with the influence function in the first place. But once you have it, then you can just check that the remainder is second order, and then you're done. So I use this as like a heuristic rule for constructing these things, but then you can check to make everything formally valid.
So just from a social engineering perspective, like if you were to derive a new influence function, you would use these tricks, but you wouldn't present this as the proof in the main paper. You would then do further work on top of that.
Yeah. To me, the rigorous way of checking that you didn't make any mistakes in this trick would be checking that that remainder in the expansion is second order, and that's kind of the settles things.
Have you ever gone through something where you thought this would work and then you checked it and it didn't?
I mean, presumably there's all this software and symbolic differentiation out there, so that must then mean that there is software for just analytic derivation of nonparametric AFs.
Yeah, I think Alex Lutka has some of this out there, but I haven't used it, so I don't know for sure, but I think he has.
Yeah, so just to add, my student has found in between your two sets, you know, the difficult one that you have to massage 4 pages, and this simple trick, the Heinz paper, it's also a review paper, I think Oliver's co-author, that point perturbation of Gattau derivatives. Pretty feasible to follow and derive.
Yeah, that's another nice way to derive these. Yeah, so this is that kind of Gattau approach, which to me amounts to picking a particular choice of submodel which has a score equal to a point mass, so that when you evaluate that derivative, you just get back the influence function. Yeah, for me, this feels a little faster, but I think different people have different preferences about these things. Okay, so yeah, I think this is maybe one of the more useful things if you haven't seen it or you want to practice some of these. I feel like, when you first start seeing some of these methods, or at least for me, some of the influence functions seem really mysterious and it's not clear where they come from, but once you do this a few times, it starts to feel natural and useful. Okay, so I've got about a half hour, so I want to make sure I get to the actual estimation side, which is how we use these things beyond the lower bound perspective. So right now what we have is this kind of lower bound argument, and we know how to construct this minimax lower bound in a pretty wide degree of generality. So all we really needed for this to work was that Taylor expansion. And for lots of the functionals that we care about in causal inference, this holds. There are some interesting examples where it doesn't. So things like conditional treatment effects, which in nonparametric models are not going to be root-in estimable, like dose response curves, counterfactual densities. For these things, this expansion doesn't hold. But it turns out a lot of these tricks are still useful. And maybe I'm giving a talk next week where I'll talk more about these kinds of issues. So maybe that's to say that there are limitations to this approximation. It is a restriction, it's imposing some smoothness, but this idea really does have use even outside of the kind of settings for which this really holds precisely. Okay, so now we have a benchmark. We know what the best possible performance is that we could achieve in these problems, but that by itself is not so interesting, right? I already gave you a lower bound before, which was just 0. I can promise you that no estimator is going to have negative error, and that's not very useful. And so now we want to actually construct estimators that can attain this lower bound. And it's not that obvious that that's going to work, because, I mean, in some ways, all of this was pretty simple, right? We constructed some one-dimensional submodel just based on this kind of pretty easy idea of just restricting the non-parametric model into some simple submodel. And it's not obvious that, we're going to be able to construct an estimator that actually behaves as well on this one-dimensional submodel as some kind of parametric thing. And a lot of the minimax lower bound arguments outside of this setting are very complicated, and so it's not obvious that this is going to work, is my point, but it turns out to work. And really, we don't need that much more. That expansion to me is going to drive the whole rest of the story. So we need to find some way to construct estimators in some hopefully general way from all of this, and then we need some way to analyze these estimators. And so that's what I'm going to talk about in the next 20-ish minutes. And I'll go kind of quickly through this. Okay. So this is the end of the lower bound benchmark story. Maybe I'll pause in case there are questions. Yeah. So I would say the influence function for an estimator, you have to show that an estimator is root inconsistent and behaves asymptotically like a sample average of something. And sometimes that may not be possible because I can't make strong enough assumptions that will guarantee the existence of a root inconsistent estimator. But if I can, then such an estimator would have this influence function. Whereas the influence functions we're talking about here are really influence functions for the parameters, and they're really just defined as the derivative in this Taylor expansion, and it's separate from data. Okay, so now we're going to construct estimators, and the main point I want to make is just, I've said this a couple of times, but this function, this functional expansion and this derivative term in particular is going to be the key part of constructing bias-corrected estimators, which have nice properties. And it's going to drive the analysis of these estimators, which again is a little bit surprising that this is going to do all this work in these three different directions, which in a lot of problems you need very different tools for all three of these different parts of the problem. Like constructing an estimator may be completely different from analyzing it. You may need completely different tools, and lower bounds might be completely separate. In my experience, that's kind of the norm. But here, this expansion really drives everything. You get all three of these pieces just from this expansion, basically. Okay, and so on the first piece of this upper bound story, which is constructing estimators, what we want to do is we have these plug-in estimators, which are really easy, right? Anytime you give me a functional, I can spit out a plug-in estimator by just taking the functional defined on P and replacing it with P hat. So they're super easy to construct. But the problem is they often have non-trivial bias. So we want to bias correct these in some way. And the reason why this expansion is useful in telling us how to do this is because it's really telling us something about the plug-in estimator. If I evaluate this expansion at like some P hat and some P, then this is telling me something about the error in the plug-in estimator. And it's saying it looks like some second order thing, which is intuitively going to be small. It's depending on squares of differences, squares of errors, or products. But then there's this other term here, which is like an expectation of something. And it's an expectation of that derivative term in the expansion. And so intuitively, if we could estimate this piece, then we could get an estimator whose, heuristically speaking, bias is going to be second order. And that's really the main idea. So this is telling us something about the error of the plug-in estimator, and once we have that expression for the error, we can estimate it, or try to estimate it and subtract it off. And this will give us a recipe for constructing estimators, and it turns out this works in quite a bit of generality. And maybe the idea for why this should work is because the expression here, it's this, it's just an expectation. And estimating an expectation is really easy. We just estimate it with sample averages. All right, so yeah, we can think about the average treatment effect example. The one plug-in estimator would take the regression function and average up those estimates. Right, the bias in this case is just going to look like the integrated bias of the estimator we use here, which in general is going to be large. It's going to be larger than 1 over root n. It will dominate things. It will give us slower than root n rates. So we want to try to do some bias correction. And from this expansion, this is telling us something about the bias. It's really telling us that it's essentially just some mean. And so we can estimate that with a sample average and then subtract it off. And now we get an estimator which should have smaller bias, and we can actually show this. So we just take our plug-in estimator and add in, really subtract off an estimate of the bias, which was negative this expectation. And so I just take that expression from the Taylor expansion, which was a mean, and replace it with a sample average. And then I have something I can actually compute from the data. It's a sample average of the estimated influence function. So it's a very simple recipe, and it works in quite a lot of generality, right? Again, we're just relying on that smoothness of the functional and no other structure really here. So yeah, this again has lots of names, one-step estimator, or in particular examples, doubly robust estimators or double machine learning. It has a long history, and you can check that it coincides with lots of these popular methods. Okay, and so this is exactly what I meant when I said that this expression, this expansion, gives us a recipe for constructing estimators, because it's telling us something about the plug-in bias, and then we just estimate it and subtract it off. And yeah, this also is in the Van Zyl text from the 80s. Here's this one-step estimator. It's the plug-in right here. Again, the typesetting is bad, and then some sample average of the derivative term in that expansion. Yeah?
My understanding is a little bit more complicated than that in terms of not just smoothness on the functional, you also need regularity in the probability distributions, like QMD.
Yeah, so I guess, yeah, Yeah, maybe it's a little bit debatable, but yeah. Yeah, there's some regularity conditions in some spots here that I'm brushing past. But I would argue in other spots we really don't need some of them. But yeah, it's a fair point. Okay, so yeah, now you have some constructed procedure for constructing these estimators. It's really easy to go through and do this, and you can get all the estimators that you'll find, say for average treatment effects or expected conditional covariances from this kind of procedure. This isn't the only procedure. You can imagine lots of other possible ways to construct estimators. So a targeted maximum likelihood does a bias correction on a different scale. But I'm going to skip this in the interest of time. Okay, so now we've got two things from this expansion. We've got a minimax lower bound, and we have a recipe for constructing estimators, but we still haven't actually showed that the lower bound can be attained by this whole procedure. And so everything I've told you in the last hour and 40 minutes might be completely useless, but that's not true. It turns out this does work in some generality. So this simple estimator, which just adds some bias correction term to the plugin, you can analyze in a very generic way, because it just looks like a sample average of some estimated function. Right, so here I'll just show you some important decomposition you can use to analyze this estimator. So here is the estimator. This is the plugin estimator, and this is the bias correction term, and then here's the target. And now I'm just adding and subtracting the expectation. This P notation means conditional expectation. For now, we've got some nuisance estimation that we need to do to estimate the stuff in the influence function. So like for the average treatment effect, we need to estimate the propensity score and the regression function. I'm going to imagine that we do this on a separate training set and condition on that. And so you can view the estimates I get from this step as being fixed, conditional on this step, and then this is an expectation conditional on that training data. That's what this P notation means. So it's just over the Z argument. So I just added and subtracted this term, and then I used the expansion. I plugged it in here. Sorry, I think I said something a little weird there. All I did here is I plugged in the Taylor expansion. So that tells me something about psi p hat minus psi p, which is that it looks like minus the expectation of the influence function plus a remainder term. So all I did was plug in the Taylor expansion, sorry. Now I'm going to add and subtract terms. So at this point, all I've done is use the Taylor expansion. I've got a centered sample average, but it's of an estimated function. So to apply like vanilla CLT type arguments, I need this to be a centered sample average of a fixed function, not an estimated one. And so I'm just going to add in what I want it to be, and then subtract that off. And now I'm at this kind of generic decomposition, which is very useful. So now I've got three terms here. This first term, this second term, and this third term. Okay, and so the first term is a centered sample average of the influence function. And the CLT immediately tells me that after I multiply by root n, this is converging to a Gaussian with a variance equal to that lower bound, the variance of the efficient influence function. And so this term is the one that we're hoping to attain. It's the benchmark. It's the one that we know we can't do better than. And so somehow what we want to do now is figure out what the conditions are that will make the second and third term negligible. Okay, the second term, so the first term is, that's the one that we hope is going to be left over. It's a simple, easy to analyze CLT type term. The second term, I call an empirical process term, as people call this, not just me. It's a centered sample average as well, but of an estimated function minus the true function. And intuitively, this one is not that bad to handle, especially if you're doing sample splitting, which is why people have started to use sample splitting so regularly in these settings. So if this estimator is even like a consistent estimate of the influence function, then intuitively this function phi hat will be getting close to phi, and so I'll be averaging something up that's shrinking. And so this is intuitively going to behave like a sample average too, but of something whose variance is going to be getting smaller and smaller. And so it should be like smaller order than this first guy, which is a centered sample average of something that's not shrinking. Okay, so under some pretty weak conditions, this guy is going to be negligible. And then the third term, which to me is really the key one, is just that remainder in the Taylor expansion. And this is what's going to dominate in general if you're using flexible methods to estimate the nuisances. Again, this one under pretty weak conditions is going to be smaller order. And because we've done this bias correction based on the influence function, this remainder is going to be second order. So it's going to look like squares of differences or products of differences. And that's why you end up getting properties like double robustness or like into the quarter rate conditions needed for these estimators to work, because if I have a product of errors in this term, if one is converging it into the quarter rates and the other is converging it into the quarter rates, then the product is going to be smaller than root n, and then this term will be smaller order as well, and I'll just be left with this guy, and I'm kind of home free. I've attained this benchmark. So this is what I mean when I say that this expansion also gives us an analysis of this estimator, because when I check that this expansion holds, I have to check that this remainder is second order. And so I've kind of already analyzed the bias, and I'm already done with that piece. Okay. So yeah, we've got these three terms. And again, I haven't restricted myself to any particular kind of estimand here. This is a pretty generic story. So I think in the last 10 minutes, I'm going to be pretty brief. I want to, maybe I'll gloss past the analysis of this guy. I'll speak briefly about it, and then maybe show you some examples of the second order remainder term, and then kind of wrap up. Okay. All right, so we want this empirical process term and the bias term to be small. And then once we've done that, then we've shown that our estimator minus the target after I multiply by root n behaves like a sample average. And now I can make this claim that my estimator has influence function equal to phi. And then I also know that I'm optimal in a nonparametric model because I showed that the best possible mean squared error is exactly the variance of this function over n in this local minimax sense. And you can construct confidence intervals and go through the usual tricks based on this Gaussian approximation. Okay. So yeah, there are two approaches that people use in general to analyze the empirical process term. It's kind of interesting, I think, historically, the way these approaches have been used. So in the earliest work in this direction, so stuff by Van Zagel and these other people I've mentioned, they used sample splitting. So they estimated nuisance stuff on part of the sample and then constructed their estimator on the other part and did simple conditioning arguments to analyze the estimator and analyze that empirical process term. They did this not for computational reasons, but because I think the arguments were simple. And then after this initial work, there was a move towards a more empirical process-based analysis of these terms where people use the same sample twice, once for estimating the nuisances and then once for estimating the parameter. And now we need to be a bit more careful because now we have, right, so you can imagine if I've estimated phi hat on a separate sample from this Pn that's from where I'm averaging things, I can just condition on that separate sample. I can use a simple like Markov inequality type analysis and analyze this and I'm done. But if I haven't done that, if I've used the same sample to estimate my nuisances and to evaluate my parameter, now I have some dependence between this averaging and this phi hat, and I need to be more careful. And intuitively, what you have to do is make sure that you haven't done something that's too complex in that sample because you're using it twice. And if I somehow fit something very complicated, that dependence is going to hurt me. And so the standard way people did this in the 80s, 90s, maybe early 2000s was through like Donsker type conditions, restrictions on the entropy of this kind of function and estimators that were used to estimate it. And then again, recently, like in the last 10, 15 years, that fell out of favor. Now, not for like the purpose of making simple arguments, but because we really have machinery now, machine learning tools, which we don't know if they satisfy these Donsker empirical process conditions, and we want to be agnostic about whether those things hold. And so we're going to use sample splitting here to just separate the role of the nuisance estimation from the parameter estimation piece and go back to the simple argument. So yeah, I think some of that history maybe has been lost, but It's kind of interesting. If you look at these very early papers, you see sample splitting just like people do today. So yeah, maybe I'll skip that, that whole story, but here's Van Zagel talking about sample splitting. Here's the idea here, probably quite a few people have seen, it's become quite popular. You just, in practice, you take your sample, you split it in half or in folds, use some piece for estimating the nuisances like propensity scores and regression functions, then go over to the part you didn't touch yet and go through this whole bias correction procedure and take your estimates that you get from the training sample and evaluate them on the test sample and estimate your parameter, and then you can repeat this across folds. People call it cross-fitting now. And then nothing really changes in the analysis of this estimator as long as you have a finite number of folds. And then I want to get to the second. So yeah, big picture, I know I'm going a bit quick. Big picture, that empirical process term, you need weak conditions to make that smaller order, and the intuition is just that it's a sample average, so it should be easy to analyze, but it's a sample average of something that's shrinking, that's getting smaller and smaller. And so it'll be smaller than that nice Gaussian term in the first piece. And then I think the really interesting piece, which is separate from sample splitting, I think sometimes people often get confused about the role of sample splitting versus the actual estimator when using these double machine learning, double robust, semi-parametric methods. But to me, these are separate. The sample splitting helps you kill off this empirical process term. The fact that we're using this bias correction is what helps with that remainder term, the bias term, in that decomposition. So they're really two separate pieces, and you need both, really. Whether you really need both is a complicated story, but okay. And so yeah, these remainders I think are quite fun to think about. And again, the remainder terms are what you check when you're checking that you didn't make any mistakes when you're running through these tricks. So you run through the influence function derivation tricks, and you come up with a potential choice, and then you check that it actually works and that when you plug it into this expansion. And the way you check that is by just checking that the remainder is second order. And then once you've done that, you'll already have the bias of this estimator, so you're done. So for some simple functionals, you get zero remainder, like for the mean, that has exactly zero remainder. This linear approximation is perfect. For the expected density, we showed this before, you get some L2P norm of the difference between your estimate, P hat and P. Here. And so that means you need to estimate the density at like into the quarter rates for that term to be smaller order, because then it's squared. So after you square an into the quarter rate, you get a root n rate. And that will make this term of the order 1 over root n or smaller. And so then that Gaussian approximation term will dominate. And so you can back out conditions like on smoothness or other structural assumptions on the density or whatever the nuisances are that you're working with to figure out what you need to get into the quarter rates, for example. For the average treatment effect, something nice happens, which is the remainder looks like a product instead of a, yeah, it looks like a product here instead of a square, and that's why we say this is doubly robust. So now we don't necessarily need into the quarter rates for both of our nuisances. So for example, if you're in an experiment and you know pi hat, you know your propensity score, you could plug that in, and this remainder would be 0. So then average treatment effect estimation is really like mean estimation. But you also have some extra leeway, right? So let's say you get faster rates for estimating the propensity score because you know something about the structure that maybe you don't know about the regression function, then you can give up a little bit of extra structure in the regression estimation problem and suffer slower than into the quarter rates there. And as long as the product is small enough, then everything's fine. Okay. So yeah, hopefully, I think the main thing I wanted to convey here is that this expansion is driving everything. It gives you the minimax lower bound. It gives you a recipe for constructing estimators, and it gives you an analysis of those estimators all in one piece. And yeah, by now I think there's lots of software out there for constructing these estimators. I have an R package that that does this for some simple approaches and for some methods that I've worked on. And you can find information on my website. I have some simple functions you can use. Test some of this out. Okay, one other thing I wanted to mention at the end here is that I hope I haven't conveyed that this story is sort of simple and solved, because it's not. There are tons of interesting open problems here. So maybe I'll just mention a couple vague directions. So one is thinking about new kinds of functionals, new parameters. So in causal inference, I think, whenever we have a new data structure, some new identifying assumptions, we can end up with new parameters, and this gives a whole new kind of expansion that maybe no one's thought about before. And so you have interesting results about what's the derivative term in the expansion, what do the estimators look like, what kind of structure does the remainder have? Is it a double or robust kind of structure? Is it something else, something different? So with every new functional, there's kind of something new to learn along these lines, even if we're using these kind of relatively well-developed tools. Another big open question is, in all of this, I said, if we can argue that that remainder term is small enough, if it's smaller than 1 over root n, then that nice Gaussian sample average term drives everything, and we're in root n land, and everything's beautiful and nice. But in practice, maybe things are so high dimensional that that remainder term is not negligible, right? Maybe I'm not willing to assume enough sparsity or enough smoothness or enough structure to say that that term is small enough. Then these estimators may not be root n consistent, and it's no longer clear anymore whether you could have done something better or not. This tells you that you can't beat root n, but you don't know if when this estimator fails, there's something that was more clever you could have done that could have been root n consistent. And in some settings, there are such estimators. So like in smoothness kinds of contexts, there are some examples where this one-step bias correction approach does not give you a root n consistent estimator because you don't have enough smoothness. And you could do some higher order corrections, like higher order influence function style corrections, which is a higher order generalization of all of this stuff that can give you root n rates. So there are some settings where there's more clever stuff that you can do that works when these things don't work. And this assumption that the remainder term is negligible is non-trivial. It's, I think I have some mixed feelings about this remainder term. On the one hand, it opens up this huge world of fitting very complicated, interesting estimators, and you can say under lots of different kinds of structure that you can get into the quarter style rates or this product rate to be small, and it's somehow a huge world beyond like parametric structure. But it's a non-trivial restriction still. It's still imposing some structure to be able to get into the quarter rates. And I think there's also a big world outside of that where maybe we can't get these kinds of rates, but we might still have some hope at constructing root inconsistent estimators. Another big avenue is what happens if that Taylor expansion doesn't hold. So I told you it doesn't hold for like conditional treatment effects and dose response curves. And actually there's lots of objects in causal inference where strictly speaking it doesn't hold, but it turns out these tricks are still useful, can still be used, but it's not as well developed, and there isn't as clear a story like there is here with optimality and so on. So there's lots of stuff to do. I think lots of fun things to work on. So I'll stop.
Thank you very much, Ted. Are there any questions?
I'll be around for a long time if people want to ask offline too.
Yeah?
So if you have tangent space restrictions, you wouldn't be efficient check, but it's kind of a pain a lot of time, and asymptotic, of course, is better, but maybe not in finite samples, because often the estimators get really complicated too, and complexity matters, right? So do you have any practical guidance about this kind of stuff?
Yeah, that's a great question. You're thinking about like semi-parametric models, is that right? I don't think I have great guidance. Maybe my preferred approach would be to actually move from a semi-parametric to a non-parametric perspective and like work with a projection type parameter or something. But maybe I'm doing that because I'm lazy. So instead of actually assuming those restrictions really hold, maybe I define my parameter as some kind of best linear approximation or something, instead of assuming that linearity truly holds. And then you're back to the non-parametric setting. But it's a good question. I think the semi-parametric perspective is for sure useful and interesting in lots of cases. And I think you're right, the efficient estimators get very complicated quickly in these models. And yeah, I don't have a great answer for how to get around that.
Okay, we'll round off there. We have, and thanks Edward again.